Imagine you're standing on the tarmac at JFK. In front of you is a Boeing 747. It's a literal mountain of aluminum, titanium, and composite carbon fiber. Fully loaded, this machine weighs nearly 900,000 pounds. That is the equivalent of 150 large African elephants, or a small skyscraper laid on its side. Common sense tells you that something that heavy belongs on the ground. Gravity is a relentless, uncompromising force. It wants that plane down. And yet, within minutes, that 450-ton beast will hurtle down a runway, tilt its nose upward, and simply leave the Earth. How? Why does the atmosphere, something as thin and invisible as air, suddenly become strong enough to support the weight of a building? Today, we're going beyond the textbook. We're going to explain how flight actually works, and why everything you thought you knew about floating in the air is wrong. Every time you settle into your seat, order a ginger ale, and stare out the window, you are participating in a miracle of Newtonian physics. But here's the cold, hard truth. It isn't magic. Aviation isn't about defying the laws of nature. It's about exploiting them. The most common misconception is that airplanes float in the air like a boat floats on water. But a boat floats because it's less dense than the water it displaces. An airplane is thousands of times denser than the air around it. If a plane stops moving, it doesn't bob on the surface, it falls. To stay up, a plane has to do something much more active. It has to move. To understand flight, you only need to master one concept: fluid dynamics. We often think of air as nothingness or empty space, but to an aerospace engineer, air is a fluid, just like water, only thinner. A plane doesn't stay up because it's light. It stays up because it moves fast enough to manipulate the air in a very specific way. This manipulation creates a force called lift. If gravity is the weight pulling the plane down, lift is the invisible hand reaching under the wings and pushing it back up. But how do you create that hand? You create it by forcing the air to move. As a plane moves forward, driven by the massive thrust of its jet engines, air rushes toward the wings. Now, look closely at a wing, or what we call an airfoil. It isn't just a flat board. It's curved on the top and flatter on the bottom. As the air hits the leading edge of the wing, it splits. Some goes over, some goes under. Because of the specific curvature, the air moving over the top is forced to travel differently than the air underneath. According to Bernoulli's principle, as a fluid, like air, speeds up, its pressure drops. This creates a pressure differential. You have fast-moving, low-pressure air pulling the wing from above, and slower-moving, high-pressure air pushing the wing from below. Think of it as a vacuum cleaner above the wing and a leaf blower beneath it. That difference in pressure is what generates lift. It is a constant, violent struggle between high and low pressure. And as long as the plane keeps moving, the high pressure wins, shoving the wing, and the 400 tons attached to it, into the sky. If the math of Bernoulli sounds complicated, let's bring it down to earth with a classic American road trip analogy. We've all done it. You're in the passenger seat of a car going 60 miles per hour down the highway. You stick your hand out the window and tilt your palm slightly upward. What happens? Your arm is instantly jerked toward the roof of the car. You didn't flap your hand. You didn't use a motor. You simply angled your hand so that the rushing wind hit the bottom of your palm and was forced downward. According to Newton's third law, for every action, there is an equal and opposite reaction. By pushing the air down, the air pushed your hand up. A wing is essentially just a very large, very high-tech version of your hand out of that car window. But lift isn't a set-it-and-forget-it force. It's a delicate balance that depends on three critical variables that pilots and engineers calculate for every single flight. Speed. This is the most important. The faster the air moves over the wing, the greater the pressure difference and the more downwash you create. This is why a Boeing 737 can't just lift off from a standstill. It needs to reach roughly 150 to 180 miles per hour before the physics even begins to work. Air density. Have you ever wondered why planes struggle to take off in Denver or Mexico City on a hot day? It's because the air is thinner. Fewer air molecules mean less pressure to work with. To compensate, the plane has to fly even faster to generate the same amount of lift. Wing size, surface area. This is why cargo planes like the C-5 Galaxy have wings that look like football fields. The more surface area you have, the more air you can catch. Here's the part that usually shocks people. A plane is technically always falling. In physics, we describe flight as a state of equilibrium. Gravity is trying to pull the plane to the center of the Earth at all times. The only reason the plane doesn't hit the ground is because its forward momentum is so great that the lift generated by the wings perfectly cancels out the weight. If the engines fail, the plane doesn't just stop in midair. It becomes a glider. It will continue to move forward, trading altitude for speed, using the air to stay controlled until it finds a place to land. You aren't resting on the air. You are surfing on a wave of pressure that you are creating yourself. This brings us to the one thing every traveler hates: turbulence. When the plane starts to shake, it feels like the ground beneath you is disappearing. But understanding the physics of lift should give you peace of mind. Turbulence is just choppy air, like waves on an ocean. It might change the air density or the wind direction for a split second, causing the lift to fluctuate, but it doesn't break the physics. The wings are designed to flex and bend. They are built to handle forces far greater than any storm. Even when the air gets rough, those pressure zones, that vacuum above and the blower below, are still doing their job. The plane isn't going to fall out of the sky because the air is bumpy, any more than a boat will sink just because the water is wavy. So the next time you're tucked into seat 22A, look out at that wing. Notice the small flaps moving, the winglets at the tips, and the way the metal seems to vibrate with power. Everything keeping you safe, every ounce of force keeping that 400-ton machine 5 miles above the clouds, is happening right there on that curved surface. It's a beautiful, invisible dance between speed, pressure, and geometry. The air isn't empty. It's a support system. And as long as we keep moving forward, the sky is wide open. Understanding the world around us makes the journey a lot less scary and a lot more fascinating. If you want to dive deeper into the engineering marvels that define the modern world, from jet turbines to the sonic boom, hit that subscribe button and join the community here at Aero Explained. Fly safe, and we'll see you in the next one.